The first fundamental theorem of calculus, something which you used to call the definite integral. So this statement is something that you're already familiar with. What happened was previously you integrate the function fx and then you put in the value of x as b followed by the value of x as a and you take the difference. So let's do a simple example for you to recall what you've done previously. Like example 28a, to compute this so-called definite integral using the first fundamental theorem of calculus, what you first do is integrate 1 over x to give you ln x. So ln x is actually termed the antiderivative of 1 over x. Over here you can see the word antiderivative is used here. And then you put in the upper limit 6 into x, and after that the lower limit 3 into x, and then take the difference. Likewise, in this function 1 to 3 of x e to x squared, you first and foremost integrate this, you get half ex squared, you put x as 3, followed by x as 1, and take the difference. Look at example C, the same thing goes. You again integrate this, the antiderivative of this is this. And again put in the first limit, put x as 1, while putting the second limit x as 0, and take the difference. Likewise, the antiderivative of cos 2x is this, and you now put in the upper limit followed by the lower limit, in this case actually 0. Another way of expressing the first theorem is you have, say, f prime. This statement is actually the equivalent of the earlier one. Just that now, if your function here is f prime, then this one is just fb minus fa. You can see the antiderivative of f prime is just f. So this statement is actually the same as the one earlier, just that it's written differently. And what's important to note is here you say that f prime is continuous on a b on the closed interval. So it becomes integrable, and then antiderivative of f prime is is f, and then put in the upper limit and lower limit. Okay, this means from this statement, right, if you integrate the derivative of f, right, you produce, you can see if you integrate the derivative of f, you actually got the difference of the two values, fb minus fa. So integrating the derivative from a to b produces what's called the change in fx between a to b. Let's look at one simple example. Your f prime is equal to this, and then you're given f0, and find f2. So you start with this statement. Bear in mind, if you bring the fa to the left hand side, this becomes fb minus fa, which is equals to the integration of the derivative statement that you saw just now. You can see I've simply brought the fa from the right to the left, and I got this. And then this is fb. So now to find fb, right, to fb, integrate from a to b of the f prime plus fa, and then use calculator to get you the answer. Example 30, if you're trying to integrate a modulus, the way to integrate a modulus is you must break into intervals from -2 to 0. Within this interval from -2 to 0, this function, right, inside is negative, so remove the modulus using a minus, and then from 0 to 1 of x, and then just perform the usual integration. Alright, give someone to take a look. Okay, let's look at example 31. Okay, during the time interval from 0 to 100 minutes, water is pumped in. So something is entering at the rate of 20 per minute, and then water is removed at a rate of so many gallons per minute. So there's actually there's in, and then there's also a out. Pump in and remove, right, at different rates. At the start, the tank has 50 gallons of water. So now to express all these things, you want to express all these things in terms of so-called integral that will help us to find the amount of water in the tank at 40. So over here, this description here, right, tells you the rate of so-called flow of water. So if you let Ft to be equal to the amount of water inside inside the tank at time t. Then F prime t is actually the rate of flow of water. There's actually an inward pump in at 20. There's actually a remover taking out, so it's a minus Ft. So the rate of flow of water into the tank is equal to in minus the out. And you can remember um, to find the to find the um, to find the value of, say in this case, right now Ft, if it brings F0 to the left hand side, Ft minus F0 is actually integration from 0 to t of this of the rate. Be very careful. You see the way things written here. If you have expression Ft, right, Ft minus F0, which means integrate from 0 to t, right? You want to realize that the integrant inside, right? I don't use t, I rename it as x. Anyway, these are dummy variables, so it's okay. But it's important for you to rename as x instead of t because you don't want to confuse with this t, which is a fixed unknown, with this x, right? So it's important for you to rewrite this as 20 minus root x. And then upon integrating and putting the limits, you get that the amount of water inside a tank is equals to this expression. And then to find, okay, so this actually for the first part question, they ask you for integral that represent amount of water in the tank at time t. Now to find the amount of water in the tank at time t with 40, which means F40, you simply put t as 40 inside here. And then use the calculator to help you. Let's look at this exercise wherein you are given the graph of y equals to f prime x. In this graph, it's made up of two straight lines, 1 and 2. In this question, you are required to find the x coordinates that give f its absolute maximum, and the x coordinates that give f its absolute minimum. And you can recall, to find the absolute value of a function, we always look at two groups of points. One group of points are the critical points. So in this graph, where are the critical points? The critical points are the points x equals to 6 and 21. 6 and 21. So now you want to calculate the value of f6 and the value of f21. By the theorem, we can say that f of 6 or fb, remember fb is integrating from a to b of f plus fa. Likewise, fb is integrating from a to b plus fa. So these are the expression for f6 and f21. So you hold on for a moment. So these are the values at the critical points. And the next thing that we look at is the endpoints. Where the endpoints, there are two endpoints at x equals 0 and x26. So the value at endpoints 0 is f0, and the value at x equals 26 is just f26, which again is integrating from 0 to 26, f prime plus the f0. So based on these four values that you have here, you have to exercise a judgment to see who is the biggest. Which value do you think is the biggest? If you look at the graph, you find that if you integrate from 0 to 6, right, you get some positive values. If you integrate from 6 to this 21, you get a big negative value. And then from 21 to 26, you get some positive value. So based on this, you can see that actually this number will be the biggest because it is the integration from 0 to 6 that gives a small positive value plus f0, although it's a small positive value as compared to this. If you integrate from 0 to 21, right, this some positive value when add on with a big negative number will become quite a big negative number. So this f21 will be f0 and some negative number. So as compared to this number is actually bigger. And then you compare with okay, between these two, of course this is bigger because it is f0 plus some positive value. But how about between these two? You look at this one, integrate from 0 to 26, right? This is some positive value, and then over here is a big negative number, right? So you can get some big negative number with some positive number, and then now you add back some small positive number. So overall, when you integrate from this all the way to here, you find that overall it should be a negative number, which means you expect this to be negative. So between these two numbers, you'll find that actually this number is bigger. So among the four numbers, this is the biggest, which means the function f attains its maximum when x is 6, absolute maximum. So when we attain the absolute minimum between these two, this is a much bigger negative number than this, because one has added on a bit more positive number than this. So therefore this number is actually smaller than this as compared to these two, right? Because this is a negative number, and therefore this number will be smaller than this. So fx actually attains its absolute minimum when x is 21, and the absolute minimum value is actually this. Okay, next we want to look at this thing called the mean value theorem of integral, and also later on the average value of a function. To start with, if f is a continuous function on a closed bounded interval, we will have this result, that the integral from a to b is actually bounded between this value and this value, where small m and big M, they are the absolute minimum and the absolute maximum of the function f. To show that this statement is true, a simple proof is provided here. If m the absolute minimum and this is absolute maximum, the function is sandwiched by these two numbers. And then you integrate throughout. This one will give you this, and this one will give you this. So very quickly you can see that the area or the definite integral from a to b is bounded by these two numbers. Now into the mean value theorem. This mean value theorem says that there is at least one c within this interval such that this integral from a to b is exactly fc times b minus a. To understand this statement, right, it's easier to see it from a diagram. Right. So on the left hand side, the integration from a to b means the area under the graph. You can see the area under this graph here. And the value on the right hand side is actually the area of a certain rectangle. Can you see the rectangle here? So the mean value theorem tells you that the definite integral from a to b can always be equals to fc times b minus a, where this is actually the area here, the area rectangle somewhere here. So the area under the graph, according to the theorem, it says can be equals to the area of a certain rectangle here. In the same diagram, are you able to spot the area of this rectangle and the area of this rectangle, which forms so-called the lower bound and the upper bound for this definite integral? And now, from this expression that we had just now, if you move the b minus a to the left hand side, if you bring b minus a to the left hand side, you get this expression. So what you have here is fc is equal to this expression. This expression, right, is actually called the average value of the function f on the interval a and b. And fc, and then c, this value c, right, is the value such that f of c is equal to the average value. Can you see? fc now is equal to the average value. So that means that this number here, right, this number here, right, is equals to the average value of the function from a to b. Okay, that is a important note you want to realize. You do not want to confuse the expression average value, this average value, and this thing called the rate of change. You can see they are different. This is just change over the interval. This is the integral over the interval. So bear in mind, integral has the meaning of sum. So it's like sum of fx over the interval. So this is average. This is change over the interval. So this gives you rate of change, average rate of change. Right. So now, for the discussion we had just now about the mean value theorem, a formal proof for the mean value theorem is actually provided here. You can actually read on your own the formal proof for the mean value theorem. It's not too difficult. Okay, moving on, let's look at some examples. Okay, in example 32, you want to find the so-called average value and then the average rate of change. To find the average value, you sum or integrate over the interval. To find the average rate of change, you take the difference and over the interval. Okay, give some time to copy first. Let's look at an example. Example 33a. In example 33a, you're given a function and you want to find the absolute minimum and then the absolute maximum of this function. For this particular case, uh, once again, to find the absolute value of a function or absolute minimum value of a function, right, you actually have to look at the so-called critical points and then the endpoints. For this particular case, we can also do it somewhat differently. When you differentiate this function, you realize that the function has a gradient that's always positive, and because the function is always and because the gradient is always positive, it therefore tells that it's increasing, which means you will attain its absolute minimum on the extreme left end and absolute maximum on the extreme right end. So immediately I have just two values. So it's unlike the usual one. Because this case, we happen to notice that the gradient is always positive. So, so we can obtain the absolute minimum and absolute maximums quite readily. Next, you're asked to find the integral and to find the you're asked to find the lower upper bound of this integral. The integral is bounded below by the absolute minimum times the interval. Remember the so-called small rectangle, and this is actually the bigger rectangle by taking the absolute maximum times the interval. So now you get the lower bound and then the upper bound. Now to find the average value of the function. To find the average value of the function, right, you have to integrate the function from 0 to 3 divide over the interval. Right, average, take the sum, integrals like kind of sum over the interval, and this is the average value. So now to justify that there is a value x so that f attains average value, we can invoke the mean value theorem for integrals. That mean value theorem integral assures us that there's always a value uh, uh, so-called fc. We use fc earlier on, right? Or fx in this case, which is equals to the average value of the function over the interval. And now if you have to actually work out the value of c or the value of x that give you the average value, you can just simply try to solve this equation. Fc equals to the average value. And you probably need to calculate to do this part of the question. Let's now look at the next example in 33b. You are given a function gx. So in this question, you are asked to find the absolute minimum and the absolute maximum value of this function gx. In this case, again, we should be looking for the absolute minimum and absolute maximum from the critical point and the endpoints. Because we know so much from a function sine x, we know that it has actually a critical point at pi over 2. And we calculate the value of the critical point at pi over 2. And then we also calculate the values of the function at the endpoints. And by comparison, this is the absolute maximum and this is actually the absolute minimum. Right, because we use all the full knowledge of what we know about sine x, we can get the absolute maximum and minimum quite quickly. So with the absolute maximum and minimum, we can now then find the bounds. The lower bound is found by taking the absolute minimum times the interval, and the upper bound is the absolute maximum times the interval. Now we get the bounds. Right, the lower bound and then the upper bound. Then to find the average value, we got to integrate over the interval and divide by the interval. The interval in this case is actually pi over 2. If you take the upper minus the lower limit, you get pi over 2. And then in this case, to find the value of x that gives you the average value of g, you simply type in the calculator to solve this. This is actually your so-called fc or fx, and this is equals to your average value that you found here, you can see. And you tell the calculator that you want to solve for the unknown x over the interval. This is a vertical slash over the interval from pi over 4 to 3 pi over 4. You should stick this so that it give you the interval, or give the value of x that's within this interval. And then when you type in the GC gives you two values. Please learn how to use the GC, right? Because you need this for the test and later on for the exam. Now let's look at integration used in kinematics. For those who have studied physics, in fact all of you should probably have studied physics up to at least your year 3, right? So not things like displacement. Xt in this case represents so-called displacement, and then if you differentiate x once, you get the velocity. You differentiate x 2 times, you get so-called the acceleration. So these are 3 terms here, displacement, velocity, and acceleration. What is displacement? This is displacement, position of particle from a fixed point. In this case, point is origin. Okay, so now if you use a first theorem, integrating velocity, right? Integrating the integrating v prime. V prime is actually the acceleration, You integrate v prime, right? Integrate v prime is you get a change in velocity, right? And then if you integrate right, this expression, right? This expression is the same as this. So it tells you that if you integrate the so-called acceleration, you can see acceleration, you get actually the change in velocity. It brings things over, right? It brings things over the other side. It's exactly the same. You can see. So note the notation is used here. We use dummy variables, not to mix up with this t here. Okay, the next thing is, if you integrate the x prime is actually the velocity, it will give you the change in the displacement. And x prime, is actually velocity. So again, you can find the displacement in time t using this. So once again, you see the change of variable names. These are dummies, not to mix up with this t here. Right, this u are the dummy variable, okay? Let's look at some example. In example 34, you are given an acceleration of this amount, and then you want to find the velocity at t equals to 5. Okay, you're given a different scenario. Find the velocity at 5 at t equals to 5 when this, and when this. So one way of finding velocity at the particular point is you can do it the good old way. You first and foremost work out the velocity expression, and then what you do is then use a condition that when t is 0, the velocity is 0 to find the constant c. Right? And then you got velocity expression. And with the velocity expression, now to find the velocity at 5, you just put t as 5. And I get this. And now we are doing the same thing is the change of velocity is actually the integration of the acceleration from 0 to 5. So you immediately work out the velocity at 5 by just bringing the v0 over. So these are two methods you can use. They're quite easy. In fact, I think that most of you are familiar with the first method. But I'd like to encourage you to think of using the second method. It's faster. Likewise, in part B, the same thing goes, You can actually do the integration first, then find the c, then with the value of c, you can find the velocity. Or you can just use the first theorem by integrating the acceleration, and then you can find the velocity at 5, at t equals to 5. And then part C, the same thing goes. Right, same thing goes. Find C separately, and then find V5 by putting t as 5. Or you can do it this way. That's a cautionary note here for you to read. Alright. Let's do an example. Example 35. So now in this case, your acceleration, and then your total velocity. When t0, the velocity is 3 meters per second. So you can calculate the change in displacement. To calculate change in displacement, right? So it means it's like you can find this change in displacement. So in this case, what happens is you first and foremost work out the velocity expression. In this case, I've integrated the acceleration to give me an expression velocity. Then using the condition when t0, v is 3 to find the value of c. And now with the velocity expression, I can find a change in displacement by integrating the velocity from 2 to 4. And then immediately I get the change in displacement. Okay, give some time to copy first. And example 36. In example 36, you're not given a function, you're given so-called table of values. These are the acceleration values and this is the time value. So now to find the, in the first part, they ask you to use trapezium rule to find this integral. So you use trapezium rule with 3 intervals. You know 3 intervals? This is 1 interval, and 2 to 3 is an interval, and 3 to 6. So you just find the trapezium at each of them. First trapezium is found by taking the sum of the two parallel sides over 2 times the so-called height or the width. Right? It is area of trapezium for the first trapezium. And this area of trapezium for the second one and for the third one. And then you work it out, it turns out to be 30. So they ask to give a meaning to this expression. This expression is actually, if you integrate velocity, acceleration, right, you get velocity. So it's a v6 minus v0. So it's actually the change in velocity over this interval from 0 to 6. Right, bear in mind, this means integrating this, right, means you get v6 minus v0, which is the change in velocity. So now they tell that the function concave up. Concave up means it's actually a smiling looking face, okay? If the graph concave up right now, and you try to draw a trapezium, you find that the trapezium will be actually bigger than the area under the curve. So because it concave up, it is actually an overestimate. The trapezium rule that you use here overestimates what you get if you integrate from 0 to 6 of this function. So if the initial velocity is minus 2, initial velocity, right, is minus 2, you don't know whether it's speeding up or slowing down. To know whether it's speeding up or slowing down, you got to compare the velocity value and the acceleration value. We are told that velocity is minus 2, right, at 0, t equals 0. Let's write the acceleration. The acceleration, right, when t0, acceleration is 7. So when the velocity value is negative and then the acceleration value is positive, right? So they have opposite sign. When the velocity and acceleration have opposite sign, we say that the particle is actually slowing down. So that's something very important to note. No? You're only speeding up if these two have the same sign, either both positive or both negative. Otherwise, it's actually slowing down. Now let's look at this thing called speed and distance traveled. If you have so-called the velocity time graph of particle, say for example, this is the velocity time graph of the particle, then the speed time graph, see, this is actually the speed, the modulus of the velocity is actually speed. The speed time graph of the same particle would be like this. You can see this is above x-axis. When this is below, right, in the speed time graph, this thing is flipped above. To find the distance traveled by a particle for duration, right? Say in this case, if you want to find the distance traveled by a particle from t1 to t2, if you're using the velocity time graph, right, then you can add up this, you can find this area separately from this area, and then add up these two areas together. Because you cannot just integrate from t1 to t2 of a vt graph, hoping to find a distance, it won't work. Because if you integrate from t1 to t2 of a vt graph, the negative portion can cancel out positive portion. and what actually you get is actually the so-called displacement rather than the distance traveled. So to use the VT graph to calculate distance traveled, you can find the area of the above and the area of the below separately. And this requires you to actually find the point where it changes, right? However, if you have the so-called speed time graph, right, uh, to find the area, sorry, to find the distance traveled, right, you can just simply take the area from T1 to T2 of a speed time graph if you have a speed time graph. Now, if the velocity function is very complicated, right, it is very hard for you to actually look for this point where the change takes place. So when that happens, and if you are allowed to use GC, right, we can immediately find the distance traveled by just doing this. Just integrate the absolute value of the velocity. So this will make a calculation much faster. You don't have to go and find those points where the velocity changes sign. Let's look at one example in 37. So you're given that a car travels this velocity, and then you want to find the average speed. Be very careful, we're asking for average speed, right? To find the average speed, we actually can find the total distance traveled first. How far total distance traveled is just integrate, integrate from 0 to 6 of the so-called speed function. Modulus of velocity is actually a speed function. You get a number of 62 and 2/3. To find the average speed, you find the distance traveled divided by the so-called duration, in this case 6. So this is how you get the average speed. To find the average velocity, you just integrate the velocity over the duration, then divide by the interval, and this is the average velocity. Right. And this brings us just before the start of the next big thing, so we stop here.